chapter K, and this is going to be Gibbs free energy. So we go to equation 12 in our course that we derived in an earlier chapter. And the equation is the differential of the internal energy per unit mass is equal to, this is the first law of thermodynamics, the infinitesimal heat transfer into the system minus the work done by the system, PD, and this is the volume per unit mass. We use alpha for that. So you can think of the bare bones of the first law as the heat transfer into the system minus the work done by the system. Now these are path dependent. The heat transfer and the work done depend on the path. You cannot say there's a heat content or work content in the system. These are inexact differentials. They depend on the path. However, we're able to express this one, the infinitesimal work done, as P d alpha, and these are good variables. They're exact differentials, the specific volume and the pressure. But the combination here depends on the integration path. But notice that when you have two of these inexact differentials, these specific ones, and subtract them, you get an exact differential where you can integrate u du and get u final minus u initial. So what I would like to do next is find a replacement for the infinitesimal heat transfer so I can at least express it in terms of good state variables. So we do that with equation 17 that we derived, and that is the differential of the entropy per unit mass, the specific entropy, is equal to the infinitesimal heat transfer per unit mass divided by the temperature. So this equation can be written as the infinitesimal heat transfer is equal to T d little s. And now I have good variables here. I have temperature and I have entropy, specific entropy. So I'm going to replace this infinitesimal heat transfer with TDS. So that will bring us to du. Now if I say energy, I mean energy per unit mass. I may not always say per unit mass, but these lowercase letters for the energy and the volume, these mean per unit mass, and the entropy here, the little s. So this would be T d little s minus P d alpha. Now I really like this equation because you can think of it as combining the first law of thermodynamics with the second law, provided we add one important thing, and that is the change in entropy in a closed system is greater or equal to 0. So with that statement, and the little s would be per unit mass. So with that statement, this can be considered a combination of the first and second laws of thermodynamics. Now we can consider this energy function here as a function, I'll say u equals, and then emphasize, as a function of the entropy, specific entropy, and the specific volume. And now let's use laws of calculus to take the differential du. We would take the partial of u with respect to the first variable, s, holding the second variable constant, and then write ds. Then we would add to that the partial of u with respect to the second variable, alpha, and we would then have the first variable being held constant, And then that would be d, the second variable, d alpha. General calculus, you might like see in calculus, z is equal to z of x and y, and then they write, dz is partial of z with respect to x, holding y constant, and etc. So now we'd like to make a table. We're going to call the first column state function. And historically, energy has been considered a state function, and we'll list that first. And I'm going to assume that here, these are all going to be per unit mass, so I don't have to write down specific every time. I'll start though here. Specific energy. And that's going to be then a symbol for that. We'll have u, little u, and then the differential, we'll have a differential for that, which will be here what we have up here. So we have the differential du is t ds minus p d alpha. And then I'm going to write down over here the variables s and alpha. Now really s, alpha, u, these are all state variables. They are variables that can describe a state. So really there is no difference between state function and these variables. But historically they have listed 4 state functions, and we put the variables over here, but don't take that too seriously since, as I mentioned, they're all interchangeable. Okay, so what we're gonna do next is have a second one, and okay, we'll just go ahead and put a little quotation here so remind it's specific. And this is going to be enthalpy. And for specific enthalpy, we're going to go to our equation 14, derived earlier. And equation 14 is the infinitesimal heat transfer per unit mass is equal to the differential enthalpy per unit mass minus alpha dp. So this equation we have derived earlier in our course. Now what I would like to do with this equation is bring in the TDS for the left side. TDS, the substitution there. And that's then dH minus alpha dP. And then the next step, I want to solve for the dH. So the dH is equal to T ds plus alpha dp by bringing the alpha dp on the other side of the equation. And this is what I want to put down for the next case. Oh, I shouldn't have written that there. I was going to mess up my table. Well, we'll deal with that. So this is h, and this is then dh is equal to t ds plus alpha dp, and then the variables would be s and p. Now what I see here is that p and alpha switched roles, switched order, say. They switched the order here. I have p alpha, then alpha dp, and a minus sign became a plus sign. I would like to switch t and s and do the same game over there. So how can I do that? Well, I can take, for example, this d of the product, ts, and that's going to be, we can write that as t, keeping the first one written down, and then going ds on the second, and then adding, put the s first, and do the dt. Now the product rule. So dt times s, that's this one here, that's the differential of the first times the second, and then here I want the differential of the second, ds times the first. So using this equation, I can then solve for t ds, And that's going to be dt times s minus s dt. So by putting this substitution in here, I'm going to get the s and t switched, all right, which is my goal. So let's do that. Then we have here du is equal to, and we replace TDS with this. This is differential of the product TS, and then minus SDT. And then we have to add that last piece, PD alpha. I want to subtract this from both sides of the equation. So I have du minus dTS is equal to then the right side minus S dt minus P d alpha. Now here I can write this as du minus Ts. These are two terms. I would take the differential of the first, put the minus sign down, and then take the differential of the second, which happens to be a product. All right, so we have that, and this is then minus S dt minus P d alpha. And I'm going to call this F, and that's the Helmholtz free energy. Helmholtz free energy per unit mass. Now the neat thing about this, and why they call it this, is that at constant temperature, that's dt to be 0, and then this is work. So when work is done, you're subtracting. In other words, you're making the Helmholtz free energy less because of that minus sign. So you can think of that as, say, delta F, write it in delta form. Delta F here would be minus S delta T minus P delta alpha. So for a constant temperature, this is gone, and the change in the Helmholtz free energy is going to be given by this work that's done. This is work. The work is done. So at constant temperature, doing work lowers the Helmholtz free energy. So you can think of having energy. Free energy is meaning the energy available for work to be done. And then as you do the work, it drops, and you get to some minimum or some equilibrium value, then you can't go anywhere. You don't necessarily go to 0, but you in a sense use up the Helmholtz free energy when there's no more left. So just think of the change as being given by this work done. See, it's subtracted. Okay, so now that we have this, we can continue our table, which we'll have to come down here and write specific Helmholtz and free energy. You can add that on there, but the specific Helmholtz function, state function, and we're going to use the symbol for that is going to be F, and then the differential, we have it right here. dF is minus SDT minus P d alpha. And now we can see that we have flipped the S and the T from up here, and notice the minus sign. We were working with the energy here, so I'm going to say that we're using this trick. We're using this trick here with the du. So we came up here, and that's where he made the substitution up in there. And then this switched the S and the T with the minus sign, and the second term stayed the same. So what are the variables here? Well, that would be T and alpha. Now we want to do the same trick for dH. So now the trick is going to be used with dH. So what we did before is we substituted for the TDS, this here, So this is going to go into here, since we have TDS, and we want to replace it with this. So that would get us DH is equal to, and now we're going to copy this down, D, the product TS, and then minus SDT, and then we got to pick up that last term, which is alpha dP. Okay, now we're going to subtract, as we did before, this differential of the product. And then we're going to look at this as DH minus TS. It's similar to this U being replaced by H. And this is going to be called little g, and that's the Gibbs free energy. The Gibbs free energy. And that's going to be equal to minus S dt plus alpha dP. But the main reason we're going to be using this later is that for a process that has constant temperature and constant pressure, for example, a phase change that we had talked about earlier in our course, dg is 0. So that's going to be the main use for G. We're not really going to be needing a Helmholtz free energy in our course, but the Gibbs will be very, very important. So if we want to add this last one, we'll say specific Gibbs, the specific Gibbs function, and the symbol for that will be G, and then the dG will be this, minus S dt plus alpha dP, and then the variables will be T and P. And that creates the 4 state functions. So we have 2 more equations we want to introduce, and what I'm going to do here is I would like to write this G function out, which is equal to H minus TS. I would then like to replace the H, which is our enthalpy, with the definition of entropy, which is U plus P alpha, which you can think of our equation 13. So using equation 13 with this that we just defined, then the G is going to be equal to U, I'll put the TS term next, minus TS plus P alpha. So here we have U and the P alpha and then the minus TS. And that equation is going to be our equation 20. Then for equation 21, we're going to use this one. This is equation 21. Here they are in a neater table with them all together. And we're 2/3 of the way through our 30 equations that we're deriving as a review of thermodynamics, with the intent to review sufficiently so we have equations that we can use to derive the moist adiabatic lapse rate. the general form that is provided by the American Meteorological Society in their glossary. See you next class.